Graphs are made up of edges and vertices. A tree is a directed acyclic graph, DAG. Directed graphs are ones that have arrows. Undirected graphs are assumed that the relationship is the same both ways. These can be looked at in a few ways. One is an adjacency matrix. Yay for matrices! You can use this matrix to show how each vertex relates to each other vertex. Using a matrix is especially useful when the graph is dense, meaning there are a lot of edges per vertices. If these edges had weights, they would be where the ones are. The zeros represent there being no relationship. In other scenarios, like if there are weights of 0 in the graph, you may need to represent that in a different way. Another way of building this is through an adjacency list. This is a list of linked lists. Each node, say C, has a linked list connected to it that says each node that are immediately adjacent to C. In order to show weights, you can make each link a tuple. While the matrix takes V squared, the linked list takes V plus E. So which you use depends on the situation. So when a graph is sparse, it's better to use an adjacency list. Which you use depends on density and which operations you are likely to be doing. As you can see from these, matrices are doing great. But as they say, I'm sure lists are good at other things. The breadth first searches nodes by depth. It uses a queue to implement this. If we start at A, then B and C are at a distance 1 because you can get there in one move. Vertex D is a distance 2 because the fewest edges that you can take to get there is 2. One way of avoiding going in a circle is to color the nodes depending on whether you have discovered them. It's like a video game where you're exploring and the map shows where you have been. We will use the colors white, gray, and black. The runtime of this is order of size of V plus size of E. First, we initialize all the vertices in Q. Next, we pick a source. Then we go in a loop to explore all the other nodes. Even if there's another path to a node that is gray or black, we don't take it because we know we have already been there. When B, C, and D find E simultaneously, we just pick one for its pi value. Depth first search explores one path all the way to its end and then works its way back. It's like the path you take when you explore a dungeon in a video game. The runtime of this is order size of E plus size of V. Dijkstra's algorithm allows us to find the shortest distance between a source and all other points. Unlike BFS, this allows us to take weights into account. This method only works if there are no negative edges. Dijkstra's is an example of dynamic programming, but we will get to more of that later. Negative edge weights are a problem because you cannot guarantee that after you take something off the priority queue, it would not be used again. We decide we are done with a vertex at some point for each vertex with the assumption that there's no ways of decreasing. We could miss the actual shortest path. The relax function is when we update a way to get somewhere with a newly discovered shortest path. For example, when we start at A, we see that it takes 4 to get to D. But once we explore further, we see that it is actually faster to go to B and then to D. S is the set of nodes whose shortest paths have for sure been determined. Q is min-Q that keeps track of the shortest paths we're currently looking at. In this algorithm, we repeatedly select vertex U, element of V minus S, with the shortest path D. And then we add U to S and relax all edges, leaving U. The runtime of this is the order of the size of V plus E, logarithm of N. This is because it's the runtime of the individual parts put together. There are 3 main lines that are costly. You could take them out, but then it wouldn't work, so don't do that. Dijkstra's algorithm starts by designating a source. In this case, we are picking A. A goes into the discovered set, and we explore its adjacencies. We choose its path to B since this is the shortest. Then we look at the possibilities out of the newly discovered vertex and update any that are smaller than previously. In this case, we see that the shortest path to C is actually A to B to C. Once we see that the path to D and the path to G have the same current number, we break the tie in some way. In this case, we will do it alphabetically. We continue the pattern until all the vertices are discovered, and we have a path that starts at the source and branches out to every vertex.